At this point, we have this tool called the derivative. We have a basic understanding of what it tells us because it tells us slope of the tangent line or rate of change or velocity. And we have a couple different ways to find derivatives. So in the last section we talked about taking the derivative using the power rule, which is a really nice way to take derivatives. It saves us a lot of time, and it makes the process of finding a derivative much more pleasant. But the power rule is fairly limited in its scope. It really, for us right now, it really only works for polynomials. And there's a couple of workarounds that we can use, but for the most part, it really only works for polynomials. And if your function is more complicated than that, then the only other way we can take a derivative is using that long limit definition, limit as h approaches 0 of blah, blah, blah. And you could continue to take derivatives that way, but it is not always the most efficient way to take a derivative. So in this section, 3.4, in section 3.5, and in section 3.7, we're just going to be focusing in on these derivative rules, and we're going to look at more and more complicated functions. And we're going to say, okay, if my function looks like this, how do I take the derivative? And we're going to see if we can generalize some of these things. So just as a quick warm-up here, I want to start by finding the derivative of f of x equals x squared minus 4x times the quantity 9x plus 8. And as this is currently written, I can't take the derivative of this because I have a product of two factors. I'm multiplying these two functions together. So that's okay, though. This case isn't too bad. I can just go ahead and FOIL this out. I can multiply these two factors together and then take the derivative of the result. So when I multiply these together, I'll have 9x to the third power plus 8x squared minus 36x squared, and then minus 32x. Whoops, I don't know why that changed to a 0. Let me fix that. And then if I combine my like terms here, I'll have 9x cubed minus 28x squared minus 32x. So here's my function f of x. I haven't actually taken the derivative. All I did was simplify this, do a little bit of multiplication, so that now in the next step, now I can go ahead and take the derivative of this result. So if I use my power rule, f prime of x, this is equal to 27x squared minus 56x minus 32. And there's my derivative. So we can deal with some cases where we're multiplying two functions together, but if we're dealing with something more complicated, like say for example we were working with y equals 3x e to the x. Well, I can't simplify this anymore. There's really not a great way to deal with this. I've got a product, right? I've got 3x times e to the x while I'm multiplying these two functions together, but I can't simplify it in any meaningful way to take the derivative. So here's where we're going to talk about the product rule, and this is a really nice one. So the product rule says if f and g are differentiable, so that just means the derivative exists at x, then the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. Sometimes I will write this more simply as f prime times g plus f times g prime. I think that just looks a little bit cleaner. But this is our product rule. This is our first kind of big derivative rule besides the power rule. And this is going to tell us how to deal with functions like we said earlier, 3x e to the x. So just to show that the product rule does in fact work, I actually want to use it on this derivative right here. So let me rewrite my derivative. F of x is equal to x squared minus 4x times the quantity 9x plus 8. So I'm going to show you how to use the product rule with a function like this without distributing, and then we should get exactly the same answer we did earlier. So what I'm going to do when I start these off is I'm going to start by labeling one of my functions as f of x and one of my functions as g of x. Usually I'll just label the first or the left-hand function f of x. So here we can call this f, and I understand, let's actually do this. I don't want to get confused. Let's call this y. Let's just say y equals x squared minus 4x times 9x plus 8. And I'm going to call x squared minus 4x, I'll call this f of x. So you can label that underneath, or even if you need to, off to the side, say, all right, f is x squared minus 4x, if it helps you to organize your information. And then I have another function, which I will call g right here. G is equal to 9x plus 8. So here are my two functions, f and g. So if I look at my product rule formula, I need f prime and I need g prime as well. So I also just need the derivatives of these two functions that I've kind of generated, that I've assigned here. So f prime, the derivative of x squared minus 4x, that should be 2x minus 4. And then the derivative of g prime, will just be 9 here. At this point, I think I have everything I need laid out. I'm going to go ahead and write the product rule right above just so that we have it in front of us. So when we go to take the derivative, the product rule says f prime times g plus f times g prime. So okay, we're going to multiply. We're going to start with f prime. So this is my derivative y prime. So f prime, that is 2x minus 4 times g. What is g? Well, g is 9x plus 8. So 2x minus 4 times 9, times 9x plus 8 plus f. So this time I want x squared minus 4x, x squared minus 4x times g prime. G prime in this case is just 9. So times 9. And I'm going to simplify this result. Again, I'm really hoping to end up with the exact same derivative that we did above. So let's see. Here I'll need to FOIL this piece out. So I will have 18x squared plus 16x minus, what do I have there, 36x minus 32. Over here I'll distribute my 9, so I have plus 9x squared minus 36x. So let's see. 18x squared and 9x squared, that gives me 27x squared. 16 plus negative 36, that would be negative 20, plus another negative 36, that would be minus 56x, and then minus 32. So this is my derivative that I just found using this product rule. And did we get exactly the same thing? Let's check. 27x squared minus 56x minus 32. 27x squared minus 56x minus 32. So we see that we have exactly the same derivative, which is good. That means that what we have works here. We can find if we can find the derivative in two different ways here, we end up with the same solution. We know that this product rule is really going to work out for us. So this is a really nice derivative rule. It's actually not too difficult of a derivative rule to prove, so I may post a proof video of this, but if I don't, there's also a bunch of them out there. If you just look up product rule proof, it's a good one just to kind of see if you can follow along, excuse me. I'm not going to ask you to prove it or, explain the proof or anything, but I do think, especially if you're planning on taking more math classes, it's good to start to kind of look at these proofs just so that you are a little bit more comfortable seeing them. You have some experience looking at them. So I want to look at just a couple more examples of the product rule here. Right now we don't have a ton to work with just because we don't have a lot of functions. And actually one thing that I want to mention back here if I asked you to take the derivative of this function, you are not required to use the product rule unless I said specifically use the product rule. But I'll tell you, I just don't ask you to do that. So you could just solve this problem by foiling it out and then taking the derivative of the result. But as we'll see in some circumstances, that just isn't an option for us. So let's look at our next example. Here I want to take the derivative. I've got square root of x, so here is one factor, times 5x squared plus 7, there's another factor. So I'm going to call this function f right here, and I'm going to call this function g. So if you need to, again, off to the side, f is equal to square root of x, f prime. Remember, this one we might need a little bit of a hint with. We said the derivative of square root of x was equal to 1 over 2 radical x. So this is, right now, this is sort of just given as a formula, but actually later on in this section we will talk about how to show that this is the case. We'll actually be able to show that this actually, give a reason for why this is. So f prime is 1 over 2 radical x. What else do we have? We have g is 5x squared plus 7. G prime then is 10x. So when I go to take the derivative, f prime, that's 1 over 2 radical x, times g is 5x squared plus 7, plus f, so now I want plus just square root of x, times g prime. Let's see, times g prime, that's going to be times 10x. From here, I don't know that I would really do a whole lot. I might just kind of clean up the way this looks. I might just say, okay, well, this is really 5x squared plus 7 all over 2 square root of x. Plus over here, maybe I'll write this as 10x square root of x, just because that's usually how we write it, but I would not ask you to simplify this anymore beyond this. So I think this is a perfectly fine, acceptable answer. If you're doing homework in the textbook or anything like that, you may see the book or other online resources simplify this further. They might try and get a common denominator right here. And so your answer might just look a little bit different than than theirs, and that's fine. I don't need you to simplify all that much. I just want you to get to a point where we don't have any like terms, we don't have any multiplication happening. We can just kind of, we've simplified it to a reasonable point here. All right, let's look at one more here. F of x equals 8x e to the x. So here, this is like that function I was talking about earlier. Here I have 8x times e to the x. There's really not a great way to simplify this. Like, there is no way around this rule other than to use the product rule. There's just no getting around it. So I'm going to call f, that will be 8x, which means f prime is equal to 8. G is equal to e to the x power, which means that g prime is e to the x. So let's apply our power rule here. Our derivative, f prime of x, is f prime, that's 8, times g, that's e to the x, plus f, well, that's 8x, times g prime. G prime, that's just e to the x. There's my derivative. So if you wanted to leave your answer like this, that's perfectly fine. I think that's a perfectly acceptable answer. I will say, though, I think it will be helpful to practice factoring, because we will, at some point, we're going to have this derivative, and then we're going to want to do more cool calculus stuff with the derivative. So we're going to want to do more algebra at the end of it, and in most cases, it will be easier if we can factor this for the types of problems that we'll be looking at. So I see 8e to the x in common between both of these two terms. I would factor out 8e to the x, and then that will leave me with 1 plus x. You don't have to factor this out. I just think it's probably a good idea to get the practice in, make sure that you understand how factoring works, just because we're going to be using it quite a bit in the next chapter. So that's really all of the examples I have for the product rule, but we will see the product rule quite a bit going forward. Here right now we just don't have, we have polynomials and we have the exponential e to the x. We don't really know the derivative of a lot of other functions at this point. So right now, I mean, any product rule that I come up with would look like one of the three that we've done here. We will be seeing the product rule a lot more going forward. The one word of caution I will leave you with here about the product rule is I think that the formula itself is not too bad. It's f prime times g plus f times g prime. So you just take the derivative of one function and then multiply it by the other, and then vice versa, add the results together. I don't think applying the formula is terribly difficult, but I do think one of the trickier aspects is just identifying when you need to use the product rule. So just try to keep an eye out here. In this first section in 3.4, I think it will be a little bit more obvious when we need to use the product rule, or the book might tell you, hey, we're using the product rule. But as we get more and more functions, I think it can be tricky to kind of pick those functions apart and pick out, okay, when do I need to use the product rule versus some of the other derivative rules that we're going to have, because we're going to keep adding more and more derivative rules. So I think this is just one more reason why practice is going to be very, very important, because as you do more of these derivatives, you'll start to gain a more intuitive sense of when you need to use the product rule versus when you might need to use another derivative rule.